All right, thanks very much. Really enjoyed the opportunity to come and tell you about some of our work in the general area of surface chemistry. I really targeted this talk more along the lines of primarily to graduate students. Some of the old timers have probably heard all this before, but it presents kind of a journey over many years looking at how to take diamond, this extraordinary material that we all know and love, and how to control the surface properties, because obviously the bulk of a diamond is extraordinary, but many of the applications that people are interested in actually requires controlling the surface chemistry. And so within my group, we work with many different kinds of diamond. We work with this wonderful blue diamond, which actually Jim Butler lent me many years ago. It's a cleave diamond, synthetic diamond, electrochemical, thin films, and nano diamond. Now, it turns out the surface chemistry of diamond, for the most part, does not depend in a sensitive way on the detailed morphology. So most of what I'm going to tell you about today is fairly generic to both planar diamond and to nanocrystalline diamond. Much of the early work was focused more on planar diamond, and some of the more recent work on nanocrystalline diamond. So the key though is how can we actually control the properties of diamond? And the challenge with diamond, as opposed to almost any other material, is that carbon-carbon bonds are really strong. And so one faces two problems. One, how do you make a material that is reproducible to begin with? And then how do you actually control the surface chemistry in a way where you can, say, control molecular layers, which has really been the focus of most of our work. All right, well, we know that we can make reproducible surfaces of diamond. The way most people make it is by hydrogen termination, and that can be done in a number of different ways. It can be done in a plasma. It can be done with nanodiamond by heating in a tube furnace and a flow of hydrogen. So that's great. We have a reproducible way of making the starting surface, but then the challenge is how do you actually do anything with this? And I'm a chemist by training, and I always make the analogy that if you remember back from organic chemistry and what you were taught, you can think of diamond as being like a giant alkane. And if you go over to your organic chemistry book, you will not find a single reaction for functionalization of alkanes. And the reason is they're really stable. And so in order to functionalize diamond, we have to provide some significant form of energy, such as radical initiators or heat or light, in order to alter the properties of nanodiamond. Um, and a key then is how do you actually control this? If you start putting lots of energy into a system, you might be able to initiate a reaction, but can you actually make it so that it stops? So that instead of forming multi-layers or polymer goop on your surface, you can actually control it and ideally make one really well-defined molecular layer. So what I'm going to tell you about today starts 21 years ago. It starts when we started investigating a method of functionalizing diamond by taking diamond samples, exposing them to a hydrogen plasma, and hydrogen terminating them. Again, just a model like right up here. And I really like to talk about this in front of graduate students because it's an accidental discovery that if we had thought about it, should not have worked. And I'll tell you about that later, why it shouldn't work, and then in fact, why it does work. But the bottom line is if you take any organic alkane, so of course to a chemist, R is pretty much any generic group, and anything that has a carbon-carbon double bond on the end, you can drip this onto your sample and you shine UV light, importantly at 254 nanometers onto it, and you can graft molecules. So we showed this back in 2000, that this was a nice way of functionalizing planar diamond surfaces. So this actually got a lot of attention very early on because, of course, if you can start functionalizing diamond with different uh, molecules, you can start then to use it as a starting point for a much more diverse chemistry. And when we started down this road, we started with this molecule that we lovingly called TFAD, trifluoroacetamide aminodesine. Um, and this has a nice little functional group on the end, which we originally chose because, well, that's easy to see by XPS because it's got a nice fluorine tag, and because this functional group can then be later, this is called a protecting group. This can later be deprotected to make a primary amine. And as any chemist knows, once you have a primary amine, you have a route to almost anything. Okay, so we did this experiment and we found that we could graft this molecule with TFAD, and then we use what is really standard chemistry in the biochemistry community to link single-stranded DNA and make DNA modified diamond surfaces. And the important thing that caught the attention of the community early on was the idea that these surfaces are just extraordinarily stable. There's been a lot of effort in the biotech community making things like gene chips or biochips, things where you can have arrays of molecules on surfaces that you can then use to sense different things in highly parallel ways. And for the most part, what you'd like to do is have surface chemistry that is extraordinarily stable so that you don't have to worry about degradation of the layers. And what we showed in this early work was that if you apply this chemistry and you link, say, a single-stranded oligonucleotide of diamond onto the surface, and then you hybridize it with the fluorescently labeled complement, and then you look at the fluorescence on the surface, and then you denature it by exposing it to urea, and then you repeat this process, that this process can go on pretty much ad infinitum. We've gone more than 50 cycles, 30 of them are showed here. Whereas if you do the same thing with pretty much any other kind of molecular layer on almost any surface, you'll find substantial degradation over time. So this idea then that we've really kind of been basing a lot of our work on is this key concept that no matter what the material is you're trying to functionalize, that carbon-carbon bonds are among the strongest bonds known in chemistry, and they are hydrolytically stable. And in contrast, silicon oxygen, silicon carbon, gold thiol, all of these surface chemistries can be degraded very, very rapidly, especially under acidic or basic conditions. And so we've been interested in this idea of making ultra-stable surfaces that then are also functional by nature of the end group on it. Now, early on, we were worried about, I pointed out the idea that, well, you have to put energy into the system. We're putting energy in the form of light. And you might ask the question, how do we know that this layer actually stops at one layer and doesn't continue to form goopy polymers? Well, one way that we did that was to take a single crystal cleaved diamond 111. This is the sample that Jim Butler kindly lent us. And we did what's called an AFM scratch off experiment. So what we did was to functionalize the entire surface, and then we go in with an atomic force microscope tip. We scan the entire region to get an image. We then go into a region in the middle and we increase the loading force until we literally scrape away the molecular layer. It actually was scraped away to the top and bottom, and you can see the buildup of molecules that were removed here and here. And then we go back and re-image along a perpendicular pathway. And we can simply look at the height change along that profile. And from that height profile, you can see that in this particular case, this is I believe, a C13 layer. But the important point is that we can directly quantify exactly how deep is that molecular layer and show that this length of 1.3 nanometers corresponds exactly to what you would expect for a molecular layer. And this is generally true, not universally true. There are some molecules that will in fact polymerize that I won't talk much about today. But the point is that this reaction, whatever it is, we do put energy into the system and it reacts, but then it stops at one layer. One of the remarkable things about this that also is interesting is that you can actually use it to photo pattern. So one way of doing that is to use a shadow mask and simply, instead of say immersing the sample into the reactant, most of these reactants are fairly expensive, so you'd like to minimize the amount of material. But if you simply take a chrome quartz mask and drip the reactant on top of the diamond surface and illuminate through it, what you find is that you can selectively functionalize the regions shown here in white, whereas the bare carbon turns out in this particular case to be black, okay, or gray. So the AFM can also be observed in SEM. I found this actually really remarkable that you can see a single monolayer with good contrast in the scanning electron microscope. And this is simply a consequence of the fact that a molecular layer can dramatically change the secondary electron yield of that molecular layer. And therefore you build up contrast, chemical contrast, even from something that's only, say, 1 nanometer thick when you view it in scanning electron microscopy. Okay, now I mentioned this was the experiment that the student did and really shouldn't have worked. And here's why the experiment shouldn't work. Normally, when you do photochemistry, you think that something has to absorb light. And yet, if you look at the reactants, here's the one that I said was kind of this magical molecule TFAD, or this other molecule TBOC. We've done this with a number of molecules. And the important point is that these molecules really don't absorb light at 254 nanometers. Um, they absorb shorter, but we're going through a silicon or a silica quartz window that doesn't pass light down at these very low wavelengths, much below 250. And likewise, diamond, of course, has have 5.5 EV band gap, which corresponds to about 223 nanometers. There's some reflective loss, but really no absorption at the wavelength that we're using for this reaction. So the question then was, how can we get reactions occurring when nothing seems to be absorbing light? And if we had thought about this beforehand, we would have said that this experiment simply would not work. Well, we did a lot of studies back in those days to begin to probe mechanistically what was going on. And one of them that we didn't really appreciate at the beginning was this molecule called TFAD that we used in that very first paper. Turns out to be very unusual. And if we look at the ability to graft other molecules, which we can probe, now probing carbon on carbon is hard. You can't use XPS very easily to quantify a molecular layer on diamond. So oftentimes we rely on infrared spectroscopy. Now infrared's pretty insensitive, but these absorbances are on the order of 10 to the minus 3, so maybe 10 to the minus 4 absorbance units for most molecular layers. But with a lot of attention, that's very doable. And the important thing here we saw here is that there are definite differences in the reaction efficiency of molecules that nominally have the same end group on the reaction end, the end that we said was reacting with the diamond surface, but the nature of this other group over here has a very profound influence on the reactivity. And in particular, TFAT is more reactive than most. Now, of course, this doesn't really make a lot of sense if the reaction is just involving this end of the molecule. Um, we know from the DNA studies that this end of the molecule is free. We know that it's exposed to the subsequent vacuum or air interface because we can do chemistry on this after we've grafted it. So we know that this end of the molecule is linking to the surface, yet we know that this end of the molecule is critically important in the efficiency of that reaction. And the question then became, why? Well, it turns out that we did some electronic structure calculations. We know that diamond has this unusual property of being a very good electron emitter and has this unusual property of negative electron affinity, which basically means that if you excite diamond with light above the band gap, it is a very effective electron emitter. What we realized was that, well, maybe if diamond is a very effective electron emitter above band gap, maybe there are pathways to sub-band gap electron emission that can actually be important in the reaction chemistry. So we did a bunch of theoretical calculations looking at the HOMO and LUMO, the highest occupied molecular orbital and the lowest unoccupied molecular orbital. It's very easy to calculate these in the gas phase using standard molecular electronic structure techniques. You have to invoke that when you go from a gas phase molecule to a liquid, that there's some additional stabilization, like a solvation energy of a couple EV. That's pretty standard. But the important thing was the ordering of the reactivity and its correlation to the ordering of the LUMO levels, the lowest unoccupied molecular orbital of these four different molecules. And in particular, the most reactive one had the lowest LUMO and the highest one had the highest LUMO. So we hypothesized that what might be happening was what is sometimes called an internal photoemission process, where we are directly exciting an electron from the valence band of the diamond directly into an electron accepting group. Normally you think this would be the vacuum level, a free electron, but suppose this is a bound electron, an electron that's bound on the end of a functional group. Well, if these are the LUMO levels, this is where an electron would naturally go. And so you might expect that there would be a correlation between the reactivity and the energy of the LUMO level if we are doing a direct electron transfer from the diamond into the adjacent molecular layer. Well, this is a nice hypothesis. The question is, could we actually prove that? Well, we set out to prove it. And the way that we did that was to set up a system where we have a diamond sample. And of course, at 254 nanometers, we're able to go all the way through the sample because it's not absorbing much. And we've also done this on thin films on different substrates. But the important thing is we set up a sample with diamond, our reactant liquid, and a platinum electrode over here. Platinum, of course, has the highest work function of any metal, 6.1 eV. So we don't expect to be ejecting any electrons from the diamond. And then we simply looked at, we could sometimes apply a small bias between these two, but we basically looked at whether there was a current generated when we shined light on this sample. Well, we did. And in fact, here is that current as a function of the photon energy, where we used a continuum source coupled to a monochromator. And then we let that light of a specific wavelength impinge on the sample. We used a lock-in amplifier to measure this because it's actually a pretty small signal. But in fact, you can see that there are, in fact, kind of two lumps to this curve. One of them corresponds roughly to the diamond band gap. And then there's an onset here that corresponds to some other process. And we hypothesize that that process is this direct photon or direct electron emission from the diamond valence band up to the up to the up to the LUMO level of the molecule. Well, again, we can make a direct correlation by measuring that photoelectron yield as a function of photon energy for different molecules. We can illuminate for a given period of time at selected wavelengths and then measure what is the efficiency of reaction down here as a function of wavelength and the nature of this molecule. And everything correlates just beautifully. That in fact, the overall reactivity of these molecules is in fact controlled directly by this electron emission process where you shine light on the diamond sample, it ejects electrons onto an acceptor level of the molecule, and that then initiates the subsequent chemistry. So the model that we have for this is shown here. Now, I'm showing the R group and the olefin, the double bond, as if they are on the same molecule. We've subsequently shown that these do not have to be on the same molecule. And then in fact, you can put in a little bit of an electron acceptor that has no reactivity, and it in fact will initiate reaction of those difficult to react molecules. For example, dodecane, which has really no ability to accept electrons. If we put in a small amount of an electron acceptor into the reactant liquid, suddenly dodecane can graft efficiently. So the mechanism then is we have this internal photoemission process where the electron ejects onto the end group of the molecule. Now we have, I sometimes refer to this as holy chemistry because we've essentially formed a hole in the diamond valence band, a cation site, and then to a chemist, this would be described as a nucleophilic. Whoop, sorry. Okay, I'll just continue on. To a chemist, this would be described as a nucleophilic attack. This is an electron-rich region of the molecule. It can attack this carbon region, and then there are other things that can happen to get rid of the hole, but basically we can form this. Now, I simply want to contrast that there have been a lot of work in other semiconductors like silicon, showing that you can photochemically graft molecules onto those surfaces. And in fact, one can imagine that maybe there's a competition where if you excite above the band gap, that you create holes in the valence band. And I'm arguing that in the case of diamond, at sub-band gap wavelengths, this can't happen, but yet this process can, this directly going to to an electron acceptor that for some reason is not showing up on the slide. And the important thing is that even though this process is relatively inefficient, it is completely irreversible. Normally, when you think about exciting across the band gap of a material, and you're going to argue that this is somehow photochemically reactive, that photochemical reactivity is controlled by the competition between the rate of excitation and the rate of recombination or other depletion of those electrons. And if this is driven by holes, then in order to have this reaction take place efficiently, you'd want a semiconductor with a long lifetime so that when you excite an electron up to the conduction band, the hole that's left behind persists for a long time. But you can pretty easily run through some numbers based on estimates of the recombination time and the available intensities of light. and show that this mechanism really isn't important under the normal conditions that we operate, and that the reason this simply works is that every electron that's emitted never comes back, and every electron that's emitted leads to reaction of one site. And therefore, if you're patient, you can have very weak intensity and eventually do this self-grafting reaction that ends in one monolayer. Okay, now what can you do with it? Early on, we showed that one approach that we were interested in was using this in applications where you're linking, say, biomolecules to the surface. But there's also been interest in doing this to provide various kinds of catalytic activity, using carbon basically as a potentially conductive and again, an ultra stable support, where the idea is that you could combine, again, the chemical stability of diamond and then confer selectivity towards specific chemical reactions by modifying that diamond surface with molecules that are known to be catalysts. And so collaboration with Shannon Stahl's group, who's been looking at using ruthenium compounds as efficient water oxidation catalysts, and porphyrins are known to be, at least cobalt porphyrin, are known to be pretty good CO2 reduction catalysts. So there are a couple of questions here. One is, well, in the grafting that I showed you, we actually have typically have a relatively long molecule tethering whatever is that active group onto the surface. And there's a few reasons why that's helpful. One is the vapor pressure is simply lower, so the material doesn't evaporate. One is that those more hydrophobic molecules generally tend to have lower amounts of water impurities or other things. And in fact, water impurities can be a problem in this. But if you follow the literature and things like self-assembled monolayers on gold, what you probably know is that electron transfer through molecular layers is generally believed to occur by electron tunneling. And electron tunneling is slow. And when you get to molecular layers that are on the order of 8 or 10 or more carbon atoms thick, that the rates of electron tunneling are so slow that those molecular layers basically are insulating. So the question we had is, well, will that be true for diamond, or will there be differences in the properties of these molecular layers that actually allow them to function as good ways of tethering electroactive species onto the diamond surface? So, okay, so we can take that chemistry and link, for example, a hydroxyl group onto the surface. One can convert that to something called an azide group using sodium azide. And then this provides a pathway toward a class of chemical reactions known as click chemistry. So click chemistry is the reaction of an alkyne with an azide group that is catalyzed by the presence of copper. And it's a very nice way of taking molecules like this and linking them to the surface. So again, we can characterize this by infrared. You can see this is a pretty weak absorbance unit, about 10 to the minus 4 absorbance units for the azide, but it's a very distinctive chemical group. We can see that largely, but not completely disappear when we do the next step. So we have confidence that in fact we're forming this triazole ring. And of course, XPS also shows that we're forming these molecular layers with pretty decent coverages for molecules that are this large. So the amazing thing we saw first off is that these are actually pretty good at transferring electrons. So we can take this ruthenium complex and we can oxidize it and reduce it. This particular one was done in a non-aqueous solvent. But you can characterize the absolute electron transfer rate by measuring cyclic voltammograms as a function of scan rate. And what we found is that this electron transfer rate through these molecular layers is on the order of 100 times or more faster than what people had typically reported for molecular layers on gold. So whereas those molecular layers on gold are insulating, these are maybe not wildly conductive. They may not be molecular wires, but they certainly do conduct electricity well enough to be able to do redox chemistry on these molecules that are tethered to the surface. The great thing, of course, is that by using this all carbon scaffold, you have incredible stability. So here's an example where we scanned through this redox process 1,000,000 times. Okay, 1,000,000 oxidations, 1,000,000 reductions, and you can see that even after 1,000,000 times, this thing is basically almost unaffected in the energies and appearance of the peaks. You can quantitatively measure that peak area or the peak height and see that, well, there's a little bit of degradation maybe, but really not very much. And even in water, you lose maybe less than half over a 500,000 cycles. And this is a very high oxidation potential. Water gets oxidized at 1.2 volts. So we're well above the water oxidation potential, straining these molecular layers to high potentials, and yet they're able to withstand this very well. These are also catalytically active, so you can take um, the functionalized diamond sample, and you can actually apply a potentiostat and do infrared spectroscopy to measure. I'm sorry, it's down here. Sorry. Here's the electrochemical. This is electrochemical CO2 reduction, not photochemical, but purely electrochemical, using that porphyrin catalyst of John Barry's group, and then measure by infrared headspace analysis. You can see very clearly the appearance of carbon monoxide, which is very distinctive from carbon dioxide. And in fact, you can even do an isotopic labeling study to show that in fact, this is coming from the initial CO2 that's present. So this actually works very well. Now, so again, I predicated this by, again, another experiment that shouldn't have worked, that if we simply believed the self-assembled monolayer on gold literature, we would have said that these layers should have been insulating, and therefore we should not have been able to tunnel electrons because that tunneling process is very, very slow. So I want to make a really important distinction, which has to do with crystallographic order. So diamond samples are, of course, crystallographically ordered, but the molecular layers that form on them might not be. And in the self-assembled monolayer on gold literature, there's an accidental degeneracy between the intrinsic optimal packing distance between alkyl chains, say in a wax or other bulk material, that optimal distance is almost exactly equal to a gold-gold distance. And so when one does these molecular layers on gold, they are so-called self-assembled monolayers because the alkyl chains of the molecules dictate the distance between the layer, and things can be well ordered because there's a good registry between that optimal packing distance and an intrinsic bond separation of the surface atoms. On the other hand, the diamond lattice is really tight. And in fact, the carbon-carbon bond distance on diamond is less than the diameter of an alkyl chain. Therefore, it's not possible to functionalize every diamond site with an alkyl chain. And in fact, you can probably only functionalize about 1 out of 6, because once you functionalize one carbon atom, the immediately adjacent neighbors are probably blocked by steric effects. So a consequence of that is that these layers are actually more disordered. They can't pack together. They can't form that night. They can't take advantage of that van der Waals interaction between the alkyl chains, and therefore we have this idea of disordered layers. And then when these disordered layers are present, well, now there's conformational flexibility. And the important thing I want to get across here is that we often think about molecular layers on surfaces as being static. We draw pictures as if the molecules are rigidly bound to the surface and they're static, but they're really not. They're really very dynamic. And when you build in a layer that has a possibility for conformational flexibility, these molecules can now actually be tilting over. This electroactive head group doesn't have to be way up here. It can actually find ways to occasionally access the surface. And given the rate at which molecules move, right, molecular vibrational frequencies are on the order of 10 to the 11 or 10 to the 12 per second. Compare that with the number of electrons that you're trying to transfer per site per unit time, and you can very easily convince yourself that it's very feasible to transfer electrons if, in fact, these molecules are flopping around dynamically um, as they're going. So my colleague Chung Shui actually did some movies where he did molecular dynamic simulations as a function of the packing of these molecules on surfaces. So these are just simple alkyl chains. The green balls are just generic electroactive groups at the end. Um, but these molecular dynamic simulations actually reproduced our kinetic data, our experimental observations almost exactly. So it's really feasible to have these electroactive groups, despite the fact that you'd think a carbon chain, 12 or 15 carbon atoms, is probably insulating. Okay, so everything up to this point, I've really focused on planar diamond, and we like to use planar diamond because it's easy to manipulate, it's easy to clean, and it is easy to quantify using methods like XPS, and you can image and do AFM and all these great things. In the last few minutes here, I want to shift gears a little bit and say, well, how do we take this and apply it to nanodiamond? Now, nanodiamond, whether it's detonation nanodiamond or NV containing nanodiamond like Adama cells, um, it's basically a powder. And a challenge with a powder is that if you try to apply this photochemical grafting technique to a powder, or say you've made a slurry or you've wet this with your reactant, is that, well, these powders are very good at scattering light. And so you might penetrate a little ways into a little mound of nanodiamond, but you're going to have lots of scattering and lots of absorption. In particular, this stuff hasn't been cleaned particularly well, so there's a lot of graphitic crap on the surface yet. But the bottom line is that a photochemical method is not really very scalable because light can't penetrate deeply enough and there's too much scattering. It can work well if you're just interested in making really small quantities. You can just disperse a little bit of nanodiamond into the bottom of a petri dish or something like that, put in your reactant, and yes, you can functionalize kind of milligram quantities. But if you want to move on to grams, then you really need to have a different way of doing this. So recently, we've been looking at another approach to this, which is to do what I'll simply call radical induced grafting. And the hypothesis here is that if you can take a radical initiator, so imagine that we're starting with a nanocarbon or planar diamond that's been hydrogen terminated. If we can actually pluck off that hydrogen, then we create a surface reactive site. And so if we have a reactant molecule like a terminal olefin present, then that can provide a pathway toward functionalizing the surface instead of light. And this could be highly scalable. So benzoyl peroxide is a really nice radical initiator. If you've ever taken Oxy-5 acne medication, benzoyl peroxide is the active ingredient there because benzoyl peroxide in the presence of light or heat can decompose and form two radicals. Okay, they're identical radicals. And these radicals are really great at killing bacteria, which is why you use it on your face. But they're mild oxidizing agents. This functional group is strong enough that it can abstract the hydrogen potentially from a carbon atom. Now the challenge is our reactants also have carbon hydrogens along the alkyl chain. So the real key then is not necessarily whether this can work. The question is really, can this work and not induce massive amounts of polymerization? Because polyolefins are made by taking olefins and adding a radical initiator, and you get chain reactions that create what most chemists call polymer goo. And generally, you don't want polymer goo on your surfaces. You'd really like to have it form one monolayer. So the key question then is there a reason to believe that this benzoyl radical might preferentially be able to abstract a hydrogen atom from a carbon on a diamond surface and do that preferentially to abstracting a hydrogen from either the olefin group, or there's hydrogens here too, right? Chemists often don't show the hydrogens, but this is a CH2 group and there's a bunch of them because this is like 8 or 10 carbons long. So the question is, can this actually give selective functionalization, or is it just going to give us, a hot sticky mess? And fortunately for us, it actually works really well. So here's an example where, again, we've turned to a fluorinated molecule at the beginning because we can very easily quantify that using XPS. And you can both look at the fluorine and you can look at the carbon. So you can very clearly see that this, in fact, is nicely functionalized with lots of fluorine on the surface. If we don't have the radical initiator present, all the control experiments show that basically there's always a tiny bit of sticking, right? But almost nothing in the absence of the radical initiator. So we have a lot of faith that this chemistry is actually working as advertised. One of the remarkable things that we've been doing over the last few years has been expanding the repertoire of analytical techniques to characterize nanodiamond. So whereas most of us who work with solid state materials are typically using things like XPS and SEM and kind of the standard materials characterizations, chemists live and die by NMR, by far the most widely used analytical technique in all of chemistry. Yet most of the time, we don't think about applying NMR to nanoparticles. So for metal nanoparticles, there's too many electromagnetic interference effects and lines broaden horribly and you really can't see anything. What we've discovered is that if you use nanodiamond, in fact, you can apply NMR to directly look at these molecular layers. So you can do fluorine NMR, you can do proton NMR, and you can do carbon-13 NMR. Here's an example where we're trying to look at, for example, if we have this terminal olefin, can we tell whether it is this carbon that links to the surface, or is it this carbon that links to the surface? To a chemist, this actually is important mechanistic information. When you have these additions to carbon-carbon double bonds, there's a class of reactions called Markovnikov and another class called anti-Markovnikov that differ in whether you are kinetically limited or thermodynamically limited in terms of what's the reactive site. The thermodynamically, the stable site for a radical would be right here on the second carbon. So if we were forming radicals on the molecule, we would expect that would be the reactive site, whereas we might see a terminal reaction if it's kinetically controlled, because this site is more kinetically accessible than that site is. So I won't drag you through all of this, but I will tell you that the net result is that we can show completely convincingly that it binds right at the terminal carbon, almost 100%. So you can get a lot of information from NMR that there's really no way you would get from these other techniques. So the question then is, why does this work? Why do we not get the sticky, gooey mess? And the answer to that largely is, well, there are actually differences in energy required to abstract the hydrogen atom from a diamond 100 or diamond 111 surface compared with the amount of energy it takes to abstract the hydrogen from an olefin or a carbon-hydrogen bond um, of a molecule. And you might think of the idea that the surface is inherently strained and that because of that, it's always easier to pluck off a hydrogen from a surface than it is to pluck that same hydrogen off of a molecule. Another way to think about it is on diamond, the hole or the radical site that's left behind can actually delocalize a little bit. It doesn't have to be located just on one carbon atom, whereas for molecules, things always tend to be more localized. So this actually makes sense from a thermodynamic standpoint. This was done in collaboration with Sarah Mason's group at University of Iowa. So this works with lots of different molecules. So these are some of them that we've shown that it actually works with. You can make charged surfaces that are positively and negatively charged, quaternary amines, fluorinated, protected aldehydes, and just like the original grafting could be expanded to lots of different forms. This could also be applied to other forms of carbon as well, glassy carbon, boron doped diamond, and carbon dots. One of the things we've actually been doing with this functionalized nanodiamond is I'm the director of a large multidisciplinary um, center that involves 15 different American universities and involves about 40 PhD students that is trying to understand the basic fundamental pathways by which nanoparticles interact with biological systems and what are the fundamental mechanisms of toxicity. And as part of that, we've been trying to understand if we take nanodiamond and we functionalize it with different molecules having different charges or different spatial distributions of charge, how does that impact the overall biological impact of the nanoparticles? And here's one example where we've taken nanodiamond tethered with different kinds of cationic groups, um, distributed in different ways. And one of these is actually functionalized with a small polymer wrap. So it's a polymeric molecule. And we looked at the viability of the cells when we expose, this is done with a bacterium called Shewanella onidensis. It's a soil bacterium, but we can look at how the viability of that, um, of that bacterium changes as a function of the nanodiamond concentration. And I'm sorry, this got chopped off, so sorry about that. Um, but we can look either at the cell viability, or we can also measure what fraction of molecules have an intact membrane. And the important thing here is that these molecules are actually relatively innocuous. They actually have very little effect on the cells. But the one that has the polymer wrap, this one, actually is very effective at killing cells. Now, do you want to kill cells? Do you not want to kill cells? That's a judgment call. I won't say one way or the other. It really depends on what you want to do. Um, but that's been an interesting sort of direction for us, is to try to understand the role of molecular structure and how that impacts the detailed molecular pathways by which cells interact, or by which nanoparticles interact with biological systems. The last thing we're doing that I'm not going to spend much time talking about, because this work hasn't been published yet, but just to give you an idea of another interesting application, is there's a lot of people right now interested in things like NV centers and nanodiamond, NV centers, SIV centers, various kinds of quantum defects, where one can imagine making various kinds of chemical sensors based on a proximity effect, in which you had, say, an NV centers in a nanodiamond, and you could selectively tether molecular radicals to a surface through some kind of chemically selective molecular linker. You could use the spin-spin interactions between that molecule and the NV center underneath in the nanodiamond as a form of chemical sensor, essentially using things like T1 or T2 or the other quantum properties that people are interested in from the NV center. And you could, in principle, read out by making use of the spin-spin interaction. Well, in order to do that, you've got to have good ways of tethering molecular radicals to surfaces. So molecular radicals are not fun to work with, right? They tend to oxidize or reduce or do other kinds of chemistry. So I'm not going to go through the details of this, but this idea of using the radical initiated grafting provides for us a pathway to make nanodiamond, or actually planar diamond and nanodiamond surfaces that are functionalized with this tempo molecule. We can prove that this works really well by looking at the XPS and or looking at the carbon XPS to look at the formation of the amide linkage, for example, and as well as looking at the nitrogen, which also gives us a pathway toward quantifying how many tempo molecules do we have. But we've then been able to go one step further and to show that these are actually spin active. And the way that I'm showing you here is by using conventional electron spin resonance in nanodiamond, where with ESR, you can see various kinds of bulk defects, as well as surface defects. But if you take those and you functionalize them with these different organic molecules, you can see that it really doesn't change the spin properties very much. But if you then take the additional steps to graph tempo, now you see quite dramatic changes. And in fact, if you do a decomposition, you can show that we are able to very cleanly extract out the molecular signatures of tempo. And again, this can also be quantified on the basis of the ESR to quantify our ability to surface tether radicals to surfaces in a very stable and very good way. So that's a future direction for people who are interested in quantum sensing, for example. Okay, so with that, I'll just wrap up. And what I hope I've shown you is that this photochemical drafting that's been kind of a mainstay for us for a number of years works really well. And we like it because it provides just unprecedented chemical and electrochemical stability. One thing that's really important to remember, especially if you're making connection to any like other kinds of molecular layers, is that molecular layers are disordered and they have a high degree of, I should say conformational flexibility. And that is an intrinsic problem or intrinsic result of the fact that there's a mismatch between the size of a molecule and the spacing between diamond lattice sites. So this new approach of doing radical grafting is a new approach that we really like now. It's a little more difficult to control. You have to make sure that you have the conditions right, or you will, in fact, induce some polymerization. But with some careful attention, this can be made to work, again, for a wide range of molecules. And it's scalable, that works for nanoparticle or nanopowders on relatively large scale. And that this can then be used to make, for example, molecular radicals for applications such as quantum sensing. So with that, I'll just wrap up. I'm not going to thank everybody who's involved, but But anyway, this is a summary of obviously a lot of people contributed little bits and pieces to what the story that I'm telling you today, a number of faculty collaborators, and this work has been supported almost entirely by the National Science Foundation. So with that, I'll just wrap up and be happy to take any questions.